Salam, peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Part 20. Foundries and Physical Implementation. The Machines That Write. Remember the language we are learning. There is one field, phi, the holophase, one continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once. Time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and a motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we listen to just one of those echoes. We stand at the threshold of Book 10.4, Reality Engineering. The first three books were the preparation: learning to read the language of phi, building the instruments to see it, and mastering the craft of writing programs for it. Now, we step out of the simulation. We leave the software world behind and enter the realm of physical consequence. We are in the foundry. This is not a metaphor. It is a building, a machine, a cathedral of controlled physics where our phi programs become real. The air may hum with cryogenic chill, or buzz with laser light, or thrum with powerful magnetic fields. This part is the grand introduction. We survey the machines that write. Your role shifts from programmer to Foundry Architect. You are learning to understand the physical platforms, their strengths, their limits, their sacred coherence budgets, that will turn our compiled intentions into indelible patterns in the world. The Foundry Hall. You walk into a vast, high-ceilinged hall. It is not one room, but many, separated by thick walls that dampen sound, vibration, and stray fields. To your left, a window reveals a chamber glowing with a soft, blue Cherenkov light, a quantum foundry, where atoms are suspended in ultra-high vacuum and cooled to within a whisper of absolute zero. Directly ahead, a clean room hums, its interior alive with the intricate dance of mirrors and lenses, a photonic foundry, sculpting light itself. To your right, behind acoustic damping panels, you feel a deep subsonic thrum, an acoustic mechanical foundry, where sound waves and surface vibrations are tamed into precise patterns. Each chamber is a author. Each takes the compiled instruction stream, the actuator commands from part 10.3.4, and uses it to nudge a specific physical phi field: the wave function of atoms, the phase of light, the displacement of a crystal lattice. Our work in books 10.1 to 10.3 was the composition of the score. Now, we meet the instruments that will play it. Our puzzle is foundational. What are the real-world hardware platforms capable of executing phi programs? How do we characterize their ability to establish and maintain coherence? And how do we match a program's requirements to the right foundry, ensuring our beautiful ideas don't shatter against the hard limits of physics? The language role, the hardware literacy skill. This part teaches a matching skill. It is the skill of bridging the abstract requirements of a phi program to the concrete capabilities and limits of a physical implementation platform. Our core question about phi is, for a given physical substrate, atomic ensemble, optical field, elastic medium, what are the fundamental limits on our ability to manipulate its phi field with precision, stability, and complexity? And how do we measure and certify a machine's performance against these limits? We are moving from writing for an ideal orchestra to assessing the actual instruments in the pit. The anchor image, the instrument maker's workshop. We will use the anchor image of an instrument maker's workshop. The different foundries are like different families of instruments: strings, woodwinds, brass. Each has a unique timbre, the physical substrate, a range, spatial and temporal scales, a dynamic responsiveness, bandwidth, and a tendency to go out of tune, decoherence. The instrument maker, the foundry architect, must understand these intimately. They must know that a violin can play fast passages, but can't hold a note as long as an organ pipe. They must match the composer's intention to the right instrument, or build a new one that can meet the demand. The coherence selection principle in foundries. In a foundry, coherence is not just a desired outcome. It is the primary scarce resource. Constructive resonance, alignment, in a foundry means the machine's internal components and the external environment are tuned to support the establishment of a clean, stable phi pattern. The platform itself is coherent. Destructive resonance, dissonance, means the platform is noisy, unstable, or leaky. Thermal jitter, vibration, electromagnetic interference, material impurities, these all inject incoherent noise into the phi field, scrambling our programs into nonsense. The foundry mantra is a statement of physical law. If coherence breaks, we stop. If coherence returns, we continue. But here, coherence breaks might be the foundry itself exceeding its thermal budget, or a vibration mode being excited. We stop the program, let the foundry settle, and only continue when its internal coherence is restored. Core mechanisms, foundry taxonomy, and performance characterization. We must systematically catalog and understand our writing machines. Foundry taxonomy, the families of instruments. We group foundries by the physical phi-substrate they manipulate. Quantum foundries. These manipulate the quantum mechanical wave function, phi. Examples: cold atom traps, Bose-Einstein condensates, superconducting qubit arrays, quantum dot arrays. Their phi is exquisitely sensitive and can encode complex superposition and entanglement, but they are fragile. Time echo. Coherence times are short, microseconds to seconds. Space echo. Can arrange atoms in precise optical lattices. Motion echo. Can simulate electron motion in custom materials. Photonic foundries. These manipulate the phase of light, electromagnetic field. Examples: spatial light modulators, SLMs, waveguide arrays, programmable metasurfaces. Their Fa is robust and fast, but typically classical. Time echo, high bandwidth, terahertz. Space echo, excellent spatial resolution, microns. Motion echo, can create propagating beams with May topology. Acoustic mechanical foundries. These manipulate the phase of material displacement, sound waves, vibrations. Examples: ultrasound transducer arrays, surface acoustic wave devices, programmable mechanical metamaterials. Their Fa is slow and long wavelength, but can carry significant energy. Time echo, bandwidth in kilohertz megahertz. Space echo, resolution limited by wavelength, millimeters to microns. Motion echo, can sculpt pressure fields and material stresses. 2. Performance characterization, the instrument's spec sheet. Every foundry must be rigorously measured against HLS standards. The lifetime of a prepared phi pattern before it decays into noise. This is the primary figure of merit. We measure it by creating a simple known pattern, a uniform phase gradient, a single defect, and watching how long it takes for the HLS measured phi to become random. This is the foundry's "how long can you hold a note" metric. Over what spatial distance can a phase relationship be maintained? We create a large-scale pattern and measure how the phase correlation decays with distance. This is the "how in tune are the strings across the whole violin" metric. Spatial resolution, the smallest feature size, defect core, gradient change, the foundry can reliably create, determined by actuator density and diffraction limits. The fastest frequency, omega, of change the foundry can implement, limited by actuator speed and system response time. Transfer function calibration. As per 10.3.4, we map input commands to output phi changes. This builds the model the compiler needs. Noise spectral density. We measure the phi noise as a function of frequency. Is it thermal, broadband? Is there a 60 Hz hum from power lines? A resonance from a cooling pump? This identifies decoherence channels. The coherence budget, the foundry's rated capacity. Before any program runs, the foundry has a rated coherence budget. This is not a suggestion, it is a safety limit. 1. Maximum stable complexity. A foundry can only support so much interestingness in its phi field before it decoheres. We quantify this as a complexity score, a function of the density of topological defects, the steepness of phase gradients, and the bandwidth of changes. Through testing, we find the maximum score the foundry can maintain for its full coherence time. This is its complexity quota. Exceeding it guarantees failure. 2. Environmental stress budget. The foundry's coherence degrades predictably with stressors. For every degree Kelvin temperature increase, T2 drops by X%. For every micron of vibration amplitude, L0 shrinks by Y%. We characterize these curves. The budget rule. Ambient conditions must be kept within the green zone, where coherence is within 95% of its optimum.
3. Actuation energy budget. Rapid, high-energy actuation can itself hit the system and cause decoherence. The foundry has a maximum power dissipation rate it can handle without degrading T2. The compiler must respect this. The foundry's operating manual is its coherence budget. To run a program, you must first check, does the program's compiled complexity score fit within the quota? Are ambient conditions within spec? If not, you cannot run. You must either simplify the program, improve the foundry's isolation, or find a different foundry. The coherence gate and rollback trigger. The coherence gate for a foundry is monitored continuously, even before a program runs. Pre-run gate, foundry health check. RETs, what we measure. Baseline phi noise, temperature, vibration levels, magnetic field drift.
Pass rule. All parameters are within the green zone of the coherence budget. The foundry is in tune. Pass. Program loading is permitted. Hezbollah. Fail rule. Any parameter is out of spec. For example, T2 measured in a quick test is 20% below nominal. Fail. The foundry is offline. No programs run. In-run gate, pattern integrity check. For long-running programs, we periodically inject a known probe pattern, run it, and measure its fidelity. Pass rule. The probe pattern matches expectation. The foundry's coherence is holding. Pass. Program continues. Hezbollah. Fail rule. The probe pattern is degraded. The foundry is losing coherence. Fail. This triggers the rollback trigger. The rollback trigger is a full stop and reset. What we do. The executing program is halted immediately. Actuators are set to a safe, zero output state. The foundry enters a recovery protocol. It may initiate a cooldown cycle, rerun its calibration routine, or perform a self-diagnostic. The partial results of the aborted program are archived with the note failed, foundry coherence loss. We do not attempt to resume. We must restore the instrument to health before any other music can be played. A measurement scene, the superconducting qubit array. Let's enact our roadmap's measurement scene. Scene, a superconducting qubit array acting as a quantum f-foundry. Goal, execute a simple braiding program, moving two defects around each other, to produce a specific measurable phase shift, a Berry phase, on a target qubit. The pass, a good foundry. 1. Pre-run gate. The dilution refrigerator is at 10 millikelvin. Qubit T1 and T2 times, energy and phase coherence times, are measured to be 100 microseconds, within spec. Hezbollah. 2. Calibration. The transfer function of each microwave control line is precisely known. Abdullah. 3. Execution. The compiled braiding program, a sequence of microwave pulses, is run. So, measurement. The final state of the target qubit is read out. Over many identical runs, to average out quantum shot noise, the measured phase shift converges to the predicted value, with an error bar consistent with the known T2 time. 5. Result. The program's intention is realized. The foundry performed as its digital twin predicted. Pass. The foundry is a reliable writer. The fail, an unfit platform. Scenario A. Each run of the same program gives a random, uncorrelated result. The qubit decoherence time is too short. The pattern is destroyed before the braiding completes. The output is noise. Scenario B. The results are consistent but systematically wrong in a way that cannot be corrected by recalibrating the existing model. Perhaps a mysterious crosstalk effect or a material instability makes the transfer function shift unpredictably from day to day. In both cases, fail. This platform cannot be trusted to execute phi programs faithfully. It is not an engineering tool, it is a scientific curiosity. The falsifiability thread has been pulled. The prediction spine, the hallmarks of an engineering-grade foundry. A reliable, calibrated foundry exhibits a clear prediction spine. 1. Twin reality alignment. The output of a calibrated foundry will match its digital twin's prediction within the twin's own uncertainty bounds, which include estimated decoherence. The real world agrees with the simulation. 2. Predictable degradation. Foundry performance, fidelity, coherence time will degrade predictably with known environmental stressors, temperature rise, vibration increase. We can plot the curve and it will be smooth and reproducible. This allows for proactive maintenance and condition-based operation. 3. Physics-limited correlation. Different foundries manipulating the same f-substrate, for example, two different optical systems, will show correlated performance limits set by shared physics. Both will be limited by diffraction. Both will have noise floors set by shot noise. Their performance envelopes, while different in magnitude, will have the same shape. Falsifiability, when machines cannot be trusted. Our falsifiability threads are brutal tests of physical realizability. Falsifier 1. If a foundry's behavior is irreproducible and unmodelable, even with exquisite continuous calibration, if it is a black box whose transfer function changes capriciously, then it is not a reliable engineering platform. It might be a fascinating physical system to study, but you cannot build a civilization on it. Engineering requires predictability. Falsifier 2. If, after exhaustive effort, no physical platform can be built that outperforms pure simulation for any practical task, if simulating a material is always cheaper, faster, and more accurate than growing it in a foundry, then phi engineering is a theoretical exercise, a beautiful philosophy without a physical footprint. This would be a profound limit, confining us to a universe of models rather than makers. These falsifiers force us to confront the material reality of our ambitions. Can we really build the pens that ride upon the world? Tri-unity in the foundry. A foundry is a triune entity by design. Time echo, coherence time T2. This is the foundry's temporal reach. How far into the future can it maintain a promise written in phi? Space echo, coherence length L0, and resolution delta x. This is its spatial grasp. How large a canvas can it work on, and how fine a detail can it inscribe? Motion echo, bandwidth delta doma. This is its dynamic agility. How quickly can it change the story it is writing? A foundry architect seeks to maximize all three, but they are often in tension. A quantum foundry may have exquisite spatial resolution, single atoms, but poor coherence time. An acoustic foundry may have long coherence time, but poor spatial resolution. The art is in choosing the right tool for the story you want to tell. Lanterns across scales. Foundries everywhere. The concept scales with our ambition. Near scale, molecular 3D printer. This is a chemical foundry. Its Fa is the molecular orbital configuration. Using scan probes or directed optical fields, it nudges molecules into bonding in specific, non-natural patterns to build novel materials atom by atom. Its coherence budget is about maintaining reaction pathway fidelity against thermal noise. Middle scale, urban fabrication hub. Imagine a district-scale foundry for construction. Using coordinated arrays of drones, robotic arms, and localized field generators for curing, bending, weaving, it executes a phi program that grows a building with optimized stress flows and embedded functionality. Its coherence budget involves synchronizing thousands of actuators in a noisy outdoor environment. Far scale, planetary scale climate foundry. This is a speculative ultimate foundry. Its phi is the planetary climate and biosphere state. Its actuators might include orbital mirrors, ocean fertilization fleets, and atmospheric chemistry injectors. Its coherence budget is astronomically complex, and its safety rails are the very definition of existential caution. This is the domain of Book 10.9. The ethics of the foundry, the responsibility of the toolmaker. The ethics of foundry design is the ethics of providing safe, reliable power. 1. Containment by design. A foundry must be physically contained. A quantum foundry's ultra-high vacuum must not breach. A photonic foundry's high-power lasers must be interlocked. An acoustic foundry's high-intensity ultrasound must be shielded. The machine itself is a potential source of incoherent energy, radiation, shock waves. It must be designed to fail safely. 2. Transparency of limits. The coherence budget and performance spec sheet are public, non-negotiable documents.
A user must know exactly what the machine can and cannot do before they submit a program. No hidden capabilities, no optimistic benchmarks. 3. Accountability of output. The Foundry's log stamps every output with its environmental conditions and self-measured coherence metrics at the time of execution. If a produced material fails later, one can check, was the Foundry in spec? This links physical outcome to manufacturing quality control. Power without a reliable, characterized Foundry is fantasy. The Foundry embodies the ethic. We will build our tools with ruthless honesty about their limits, for they are the hands that will shape our world. The recognition skill, seeing the Foundry in the wild. You know you need this skill when you see a physical system that seems to hold a pattern against noise. And you ask, could I program that pattern? The intricate, stable flow in a superfluid helium experiment. The perfect repeating interference pattern from a laser array. The self-organized standing wave in a vibrating plate. These are proto-foundries. They are physical systems already manipulating a phi field with some coherence. Your eye is now trained to see not just the phenomenon, but the platform potential. What actuators control it? What is its coherence time? What is its noise floor? You're looking at the world and seeing not just what is, but what could be made. The master tree location. This part, 10.4.0, is the massive root system of book 10.4. It depends entirely on book 10.2, measurement calibration HLS, to understand and certify the foundries, and feeds essential models to the compiler 10.3.4. It is the hardware foundation. It enables all of book 10.4 that follows. Material design 10.4.1, field sculpting 10.4.2, defect engineering 10.4.3, and patch creation 10.4.4. Without knowing our machines, we cannot engineer reality. This is where theory touches matter. Return to the phi. Let us zoom out. A phi foundry is a machine designed to create localized, coherent structures within the universal phi field. It is a lens that focuses our intentionality into a specific physical substrate. The foundry itself is a grand phi structure, a pattern of containment, control, and measurement that must be coherent in its own right to function. We are not building machines that violate physics. We are building machines that exploit physics with supreme precision to make manifest a tiny fragment of the infinite possible coherence that the single field phi contains. Zenodo and the equations of the foundry. If you want to see the full mathematical derivations and exact equations behind this idea, you can search for Holophase on Zenodo. There, you will find the scientific papers that this audio journey is built on. The papers detail the quantum master equations that define T1 and T2 times, the diffraction integrals that set photonic resolution limits, the elastodynamic equations for acoustic coherence, and the statistical methods for characterizing noise spectra and deriving reliable coherence budgets from empirical data. They provide the rigorous physics that turns the workshop of instruments into a quantitative engineering discipline. Closing. So, picture yourself back in the foundry hall. You're no longer just a visitor. You understand the hum of the quantum chamber as the sound of atoms holding their phase against entropy. You see the dance of light in the clean room as the pen strokes of a photonic scribe. You feel the deep thrum to your right as the slow, powerful handwriting of acoustics. You have a program. It specifies a pattern of topological defects in a spin or condensate. You check its complexity score against the quantum foundry's quota. You verify the fridge temperature is in the green zone. You load the compiled pulse sequence. You press execute. In the chamber, invisible to the eye, a ballet of microwave and laser pulses unfolds. A new knot is tied in the fabric of reality. You have just learned to match intention to implementation. You have met the machines that write. This is part 10.4.0, Foundries and Physical Implementation, the machines that write. It is the grand opening of book 10.4, Reality Engineering. In our next session, we will use these machines for our first concrete act of creation, Material Design 10.4.1. We will learn to treat solid matter as frozen phi, and use our foundries to write novel materials into existence, atom by atom or meta-unit by meta-unit. We will move from understanding the pen to writing our first word. Remember, One field phi, with its infinite echoes. We have now built the hands that can touch it. Our conversation with reality is about to leave permanent marks. Salam, and peace be upon you.